Hi everyone. This is that long-awaited multiple choice from like many weeks ago. All right, so here's number one. An object slides across a horizontal surface. As they show, it moves to the right and it slows down due to the force of friction. So we know we have to include that. So we want to know which of the following free body diagrams could represent the forces. So just in general, what we know is the direction of displacement is horizontal, which means the vertical forces, if I'm just going to draw, the vertical forces need to balance, and there's a force of friction. It's moving to the right, so the force of friction is going to point to the left. So if I go through A, these are balanced, F normal and F gravity, force of friction is pointing to the left, so that's it. But if we look B, these are not balanced. In C, those are also not balanced, the vertical forces, normal force and gravity. And in D, force of friction is pointing in the wrong direction. All right, number two, this is probably the hardest one, I would guess. So we've got a free body diagram above. There's a 5 kilogram box, that's our mass. It's being pulled to the right. And let's see, we gotta focus this a little bit better. By a string that's at an angle of 30 degrees above the horizontal. The coefficient of kinetic friction is 0.3. The tension is most nearly. So here we go, constant speed F net equals 0. And what we know about that is that the forces are balanced. So let's take a look at these forces. First of all, we know mg down here is going to be 50 newtons, because that's 5 times 10. And we're going to call tension Ft, force of tension. And we're going to divide it down into its components. So this is going to be Ft sine 30. And the horizontal part of it is going to be Ft cosine 30. Great. Okay, forces are balanced, so let's do vertical forces. Ft sine 30 plus normal force is going to equal 50. Plus normal force equals 50. And then horizontal forces. Force of friction is equal to Ft cosine 30. Should have written those next to each other instead of on top of each other. Oh well. Okay, so let's simplify these down, actually. Okay, sine 30 is 0.5. So here we've got 0.5 Ft plus normal force is equal to 50. Great. Over here, force of friction is mu normal force. That's equal to square root of 3 over 2 cosine 30. And we know mu is 0.3. So we've got 0.3 normal force equals square root of 3 over 2 Ft. Sorry, guys. So we've got two equations, two unknowns. We're going to solve one of these for normal force. I'm going to solve this one on the right. Divide by 0.3. Divide by 0.3. Divided by 0.3 is the same thing as multiplying by 10 over 3. So I'm just going to keep it as a fraction because that's easier. That gives you 5 square root of 3 over 3 Ft. Okay. So I'm going to plug that in up here for normal force. So I've got 0.5 Ft plus 5 square root of 3 over 3 Ft equals 50. So you add the like terms and then do 50 divided by whatever the coefficient there is. That's a lot of fractions. So I'll just give it to you in the decimal form. So square root of 3 times 5 divided by 3 plus 0.5. So you end up with about 3.4 Ft equals 50. So when you divide that out, you get about 14.76. And when we go down, we see that we don't have 14.76. Most likely, instead of 50, they used, instead of 10, they used 9.8 or 9.81. So we're going to go with that one there. All right. Next, we've got a box that's given a sudden push up a ramp. Friction between the box and the ramp is not negligible. Which of the following best represents the direction of the actual forces acting on the box as it moves upwards after the push? So there's no F push. I'll just draw the incline like they do. I'll draw that. Okay, so this is the box. We know force of gravity points down. We know normal force X on the box, and that's going to be perpendicular, so that's normal force. And it is moving upwards, so we've got force of friction. That's what it should look like. Let's take a look. Oops. Sorry, guys. Okay. Whatever. You guys saw what it is supposed to look like. So we've got this A, which looks like it's supposed to. Normal force, force of friction, force of gravity. Super. Let's check the other ones. This is wrong because what the heck is that force? Goodbye. They're tricking you. They wanted you to think it's force of the push. This is wrong because they wanted you to think that, oh, it's moving upwards. There's got to be a force pointing upwards. There doesn't. Whoops. This is wrong. That's all wrong. Everything wrong, pretty much. And then this one, no. See ya. Goodbye. It's A. Okie doke. An object travels down a ramp at a constant acceleration. Remember, this is different than constant speed, not F net equals 0. Okay, not. So that's a no. Because it says constant acceleration just means A is something. The object experiences a force of friction and a gravitational force, which of the following could be true about the motion of the object. Okay, so the force of friction between the surface and the object is less than the component of the gravitational force that is parallel to the ramp. If the object increased in mass, the object's acceleration would change. If the object increased in mass, the normal force would remain the same. The force of friction acts in the same direction as the object travels. Oh, I forgot I can freeze this. Okay, sorry guys, I was entertaining myself only. So we know this is wrong because that doesn't happen. So let's see what's going on for these last three, okay? So let me just draw. It's traveling down a ramp, right? So this is displacement. We know force of friction would be pointing that way. Normal force would be pointing that way, and force of gravity would be pointing this way. Okay, so what we're looking for here, and it's got a constant acceleration, F net equals ma, which means just basically, that the acceleration it has, so F net is going to be force of friction, and that's equal to the mass times this constant acceleration. Okay, what we know about this is we know, I'm going to divide out I'm going to put the force of gravity into its component forms. So this is Fg cosine theta. This down here is Fg sine theta. I had told you guys about the trick that if it's on a ramp, that it doesn't seem like it should be, it seems backwards, but the part of gravity that points down the ramp, think of it as sliding down the ramp, that's the sine, okay? So anyway, we know that force of friction is equal to mu times the normal force. The normal force is Fg cosine theta. So we know mu, and Fg is mg. Mg cosine theta equals ma. Okay, so this is what we know. So let's take a look up here. It says the force of friction between the surface and the object is less than the component of the gravitational force that is parallel to the ramp. Well, that's Fg sine theta. That's the part that's, so this is, possible. The next one, if the object increased in mass, the acceleration would change. So down here we know acceleration actually is just mu g cosine theta, so that, because mass cancels out, so that's wrong. If the object increased in mass, the normal force exerted on the object would remain the same. No, because normal force is equal to the Fg cosine theta, which means mg cosine theta, so if the mass increases, then normal force would increase. So it's got to be this one. Okay, my bricks here. 2 bricks are on the floor. This is the force diagram for brick 2. The forces are an upward normal force, that's from the floor, the downward force exerted by brick 1, and the downward gravitational force. How many forces, if any, in the force diagram are contact forces caused by microscopic interactions? There's 2 contact forces. There's normal force and force number 1 based on the brick, because those 2 things are in contact. Gravity is not a contact force, so only 2. C. Okay, number 6. This was actually maybe a tough one too if you didn't know what to look for. We've got 2 blocks of the same mass but made of different materials slide across a horizontal rough surface and eventually come to rest. A graph of the kinetic energy of each block as a function of position along the surface is shown. Which of the following is a true statement about the frictional force that is exerted on the 2 blocks? Let's break this down. We've got a block, let's say it's moving this way. We know force of friction would point that way, and we've got normal force and force of gravity. Those should balance out. Maybe this needs to be a little higher. Great. And eventually it comes to rest here. And it would just have force of gravity and normal force. Okay. The energy here at the beginning is going to be kinetic energy. The energy here is 0. So here's what we know. We know kinetic energy plus, let's see, we know work is equal to the change in energy. We know, which is final energy, 0, minus initial energy, K. So the work here is equal to negative K. You might be like, how does that help us? Well, if we look at what's doing work, force of friction is doing work. That's the only thing that's doing work. So our work, which is equal to F d cosine theta, which is just force of friction. So our work, our negative K, is equal to the force of friction times displacement. So our force of friction is equal to negative K times displacement. Here we go. If we go over here, we've got a kinetic energy position graph, which is pretty much here, kinetic energy, displacement. So our force of friction is going to be equal to the opposite of kinetic energy divided by displacement, which happens to be the slope, right? So here, if we do change in kinetic energy over change in position, that's kinetic energy divided by d displacement or position. And so force of friction is just the opposite of it. So we've got, let's just use the blocks, right? 1, 2, 3, 4, 5. So this is, let's see, down 5 over 2. So this is negative 5 over 2. So the force of friction here is 5/2. And then over here we've got down 5 over 4. So the force of friction is 5/4. Okay. So if we're comparing, right, so let's see, we need to compare, does force of friction equal 2 F1 or 1/2 F1? Well, we've got, force of friction 2. So this is twice as big as that one. So force of friction 2 equals 2F force of friction 1. So this is wrong and this is wrong. Okay, since the force of friction is represented as the slope of each of the 2 curves, since the force of friction is represented as the inverse of the area bound by each curve, well, we use slope. So, boom, there you go. Okie doke. A student wants to determine the coefficient of static friction, mu, between a block of wood and an adjustable inclined plane. On the following, the minimum additional equipment the student needs to determine a value of mu is. Boom, boom, boom. There you go. So here we go. Let's talk about this. Oh my God, you guys. We've got normal force, we've got force of friction, and then since it is static, the force of friction, oh my God, force of gravity down there. Okay, great. Normal force, force of gravity, force of friction. Okay, so here we go. We know that if we break this down, if this is at rest, that means that the force of friction is equal to Fg sine theta. Okay, so this is going to break down to 2 component forms. This is Fg sine theta. This is Fg cosine theta. And that normal force is equal to Fg cosine theta. We also know We also know that force of friction is mu normal force. So that's how we're going to get mu. So force of friction equals mu normal force. So that means that Fg sine theta is equal to mu times normal force, which means that mu is equal to Fg sine of theta over Fn. And we know that normal force is equal to Fg cosine theta. So we've got mu equals Fg sine theta over Fg cosine theta. Okay, which just means those cancel out, which means mu equals the tangent of theta. So it looks like all we need is to find the angle. And so that means we just need a protractor. Next one. The inclined plane in the figure above has two sections of equal length and different roughness. The dashed line shows where section 1 ends and section 2 begins. A block of mass m is placed at a different location on the incline. The coefficients of kinetic and static friction between the block and each section are shown in the table below. Well, that didn't show up when I printed this off, you guys. Oh well. If the block is sliding up section 2, what is the magnitude of the force of friction exerted on the block by the incline? All right, hold on. Let me scroll and get my information. Oh, it still doesn't. What number is this? Number 8. I'll find it. Okay, so we are talking about sliding up. So this is kinetic friction. And what we know is that in section 1, we've got mu k. And in section 2, we've got 2 mu k. Great, super. If it's sliding up section 2, what's the magnitude of the force of friction exerted on the block by the incline? Okay, so here we go. We've got, oh shoot, I can't see. Yeah, you guys can see me. This is Fg, Fn, it's sliding up, F friction. Okay, so again, we know the force of friction is equal to mu normal force. We know force of friction is equal to 2 mu k normal force. All right, normal force is equal to Fg cosine theta, which means that force of friction is equal to 2 mu k mg cosine theta, which is A. If you don't know why Fn equals Fg cosine theta, again, we've got the little trick. Oops. I told you guys that Fg sine theta is sliding down the ramp, so that means the other part of it is Fg cosine theta. Okay, some students want to calculate the work done by friction on an object with an unknown mass as it moves along a straight line in a rough horizontal surface. The students have a force probe, a meter stick, and a stopwatch. Which of the following will allow the students to take the measurement to calculate the work done by friction? All right. So we've got, let's call this the rough horizontal surface. Boom. Here we go. Fg, Fn. Force of friction. We want to know the work done by friction. Sorry, yep. Okay, we don't know the mass. Mass equals question mark. And we want to know the work. So we can measure our force. We can measure the distance because we've got, I'm just going to write this down. Force probe. We've got a meter stick. And we've got a stopwatch. Okay, so what we know is we know that work equals the change in energy. Also, it's either change in energy or Fd cosine theta. Okay, here's the deal. We can measure D with the meter stick, and we can measure F with the force probe. We cannot, and then cosine theta is going to be, that's going to be gone. It's just going to be Fd, because cosine theta is going to be 1 because we're moving 180 degrees. Or 0 degrees, whatever. It's the same. So anyway, so we've got to figure this out, right? So if we, so I said force probe measures the force. If we pull, so we can measure our pulling force. If we want, right? So let's say this is now F pull. Okay. So F pull is going to equal F friction if we're moving at a constant speed. Because that would be when F net is 0, when acceleration is 0. Okay. And so if we can make our F pull, if we can do a constant speed, we know F pull and F friction are going to be the same, and we can multiply that by the distance. So let's see. Unknown constant acceleration, no. Unknown constant speed for a measured time. Time's not going to help us. We need displacement, no. Unknown constant acceleration, no. So it's going to be this last one. Unknown constant speed at a measured distance. All right, last one, my friends, last one. An object is released from a large height above the ground, takes a very long time to reach ground. The only forces exerted on the object are the force of gravity and the force of friction. The speed as a function of time is shown above. Which of the following best claims that describes the force of friction exerted on the object? Okay. So show you guys the answers here. All right. So here we go. So it says that it is initially 0 and increases until it's equal to the force of gravity. It's initially equal to the force of gravity and decreases until it is 0. It's always equal to the force of gravity. It's always greater than the force of gravity. So what we know about if something were to fall down without force of friction is that this would just increase like infinitely, right? Okay, so V would increase infinitely. Okay, so it would just kind of keep going on this path, but eventually it starts slowing down. So we know the force of friction here, this is making this pretty much slow down, right? This is so this is when the force of friction is almost equal to the force of gravity, because it's keeping it at a constant speed. Over here, force of friction is very low. So when we look at our answers, it's initially 0 and increases until it's equal to the force of gravity. That seems right. It's initially equal to the force of gravity and decreases until it's 0. Nope. It's always equal to the force of gravity. Nope, it wasn't at the beginning. It's always greater than the force of gravity. Nope. Otherwise, it wouldn't speed up, so it's A.